This is a robotic shoulder, but inside it are human cells undergoing a vigorous exercise routine. This setup has been developed to mimic the conditions of the human body, where cells can be pushed and pulled and stretched in different directions. If it works, one day human patients could be treated with tissue grafts grown in robots. Growing cells in a lab is easy enough. They need nutrients, oxygen, and something to grow in or on. A Petri dish, for example, can give cells everything they need to thrive. For Pierre Moutuis, however, a Petri dish wasn't quite enough. Pierre wants to grow tendon cells, the tough bits of tissue that connect muscles and bones. He hopes lab-grown cells could one day be grafted into human bodies to repair tears in shoulder tendons, for example. But there's a catch.
We are still far away from a fully functional tendon tissue grafts, and we think that partially this is because we are not providing the same complexity of mechanical stresses around those cells.
A Petri dish is not the natural home of a human cell, and it seems that some cells need an environment that's a little bit more stimulating.
What researchers have shown for a long time now is that external mechanical stimulation is really key to mature the tissue properly and to have the cells express the right type of genes and to produce the right extracellular matrix.
Instead of a Petri dish or bioreactor flask, researchers grow tendon cells on stretchy plastic scaffolds, with fluid providing the oxygen and nutrients. This small chamber is Pierre's team's new flexible design. So far, scientists have used repeated stretching and relaxing to stimulate the cells to grow properly. But unidirectional stretching like this is pretty different from what tendons would experience in a real shoulder.
What the body is providing to native tissues is multi-axial mechanical stimulation, where you have three-dimensional mechanical stresses being applied to tissue construct in the form of not just tension, but also compression and torsion.
Pierre's new chambers can be pushed, pulled, bent and twisted, just like a real tendon. But he still needed something to do all that pushing, pulling, bending and twisting. What he needed was a robot.
What you're seeing here is a robot, and that's a humanoid robotic avatar. And what makes them special is that they have muscles and tendons as we humans do. So we try to imitate the way the human body works. And we're doing this because we believe it's going to help us build robots that are eventually going to move just as natural and graciously as human bodies do. They're being used in research, neuroscience, biomechanics, and so on. But eventually they might be used to build better prosthetics and test new implants.
These robots are intended to mimic the shape, the dimensions, and the mechanics of the human body.
And one day I got an email from a certain Pierre Moutuis in my inbox asking me whether I'd be interested of using his robots to put tendons on top of them and grow them. And of course I was like, hell yeah, that's exactly in line with where we want to be going eventually.
Pretty soon, Pierre's lab had their very own robot shoulder.
So what you can see is that one side of that chamber is being attached to the humerus heads, so the bone-like structure that you see on this end, and the other side of the chamber is attached to a string that is then linked to the motor, which is acting as a muscle.
But Pierre wasn't satisfied with an arm that just moves up and down.
So this is now a newer version of our robotic shoulder. It allows us a more complete range of motion of the human shoulder, so not just abduction, but also this sort of rotation. And you see that now the arm is moving in multiple directions.
This new method was designed to grow tendons to graft onto shoulder injuries, but there are other possible applications.
To look at improving rehabilitation exercises by looking at how the cells are being affected by a particular exercise, or it could also be used in translational research to screen through biomaterials to ensure that they are mechanically suitable for humans.
Now that they've developed the system to make it work, The team's next step is to figure out whether this new robotic Petri dish can actually grow better tendons than the old-fashioned method.
So this has been years of work already, and obviously now we've demonstrated that it is feasible to use this approach. And I think the fun only starts now, because now that we've demonstrated that it's feasible to use those humanoid robots, we can explore the different possibilities that it can do and look into whether it can really help to improve the quality of the grafts by providing these more physiologically relevant mechanical stresses.